Hey guys, welcome back. So today is day 7, and today I'm going to give finally um, the last description or last interpretation of this thing that we've been talking about for so many days now, the derivative. I'm going to give one more sort of perspective on it, one more formula. Before I do that, of course, I'll go over a couple of problems from the worksheet. So I'm going to share my screen and we'll go over some of those together. So here's the worksheet from yesterday with the work that I did on the PDF during yesterday's video lesson. Let's go ahead and do some of these problems here. So we've got some function f, and I want you to state the intervals or points on which, first of all, the derivative is positive. So where's that happening? Well, the derivative, of course, is the slope of the tangent line, right? That's what we established yesterday. And so you're just asking, where is the slope of the tangent line positive? Well, is it positive here? I mean, it certainly seems that way. So yes, it's positive there. And it's positive here, and it's positive here. And the slope of the tangent line is positive here, all the way up to here, right? Because the slope seems to be 0 there. And then after that, the slope appears to be negative for a while. And then here it's 0, and then the slope is positive again. So where is the derivative positive? Well, it's positive here, right? That's where the slope of the tangent line is positive on that interval. So up to like from negative infinity all the way up to here, like negative 1.5. And then it's positive again from positive 1.5 all the way up to positive infinity on this region here. A trickier problem, of course, is something like C or D. C is asking, where is the derivative increasing? Well, here the derivative is positive, and in fact, it's quite positive, right? It's a rather steep positive slope line. So maybe the slope is like 3 here. And then you'll notice the slope is still positive, but a little bit less positive. And then here it's still positive, but a little bit less positive, right? And then it's 0, and then it's negative. So all along this, this region, the slope appears to be decreasing, right? But then somewhere in here, the story changes. Like from here, from here up to here, right? Right here, the slope is certainly negative, right? But then a little bit further along, it's 0. So certainly it's increased along that interval. And then along here, now it's positive, and now it's more positive. So the slope does appear to be increasing. That means the derivative is increasing along this region here. And so maybe from 0 to positive infinity, I think, is probably where. Okay, fine. So yeah, and then these problems, I ask you to so what is f prime of -1? You just go to -1, you draw a little dot, you do your best to draw a good tangent line. Maybe it's something like this, right? And then you do your best to try to figure out what is the slope of that line. Not really that obvious, right? As I said, your answers are going to be very approximate. I think, I mean, it's obviously negative. I don't think it's as steep as -1. -1 would be like this. So maybe it's like -1/2, right? Something like that. I mean, you don't worry about getting the answers exactly right because it is very approximate. But I did want to talk about some of these, fill in the blank. If the derivative is positive on an interval, then the function is increasing or decreasing. It's actually going to be increasing, right? I mean, as you can see, whenever the function is increasing, like the function's going up along this entire region, notice that the slopes are all positive. And whenever the function is decreasing, like along this region here, notice that the slopes are all negative. So that's really a quick way of seeing it. When the derivative is positive, the function is increasing. And when the derivative is negative, the function is decreasing. Maybe just a few of these here. Sketch a curve whose derivative is positive and increasing. I mean, I give you the answers. Here's a picture. So I claim the derivative is positive and increasing throughout this interval. Well, the derivative certainly seems to be positive the entire time because all of these slopes are positive. And if you look, yeah, the slopes appear to be increasing as well, right? Because first it's positive, but only a little bit positive, and then it's more positive, and then more positive still. So yeah, positive positive and increasing. On the other hand, if I go to like number 6, it says sketch a curve whose derivative is positive and decreasing. Okay, so the slope should be positive but decreasing. That's this picture here. I mean, if you look, the slopes are certainly, the slopes of the tangent lines are certainly all positive, right? They're all positive along this region, but yet the slopes are decreasing, right? Because right here, the slope is very steep. It's a very large positive number. And then it's a less positive number and a less positive number. So positive, but decreasing. I think it's really worth, trying to wrap your head around these. It's hard the first time that you go through these, but the more that you try problems like this, the better you'll get. Okay, so with that in mind, I'm going to return to actually basically the diagram that we worked with yesterday. This is the diagram that we worked with yesterday to derive the fact that the slope of the tangent line is the derivative. And I'm basically going to do the same thing today, except all I've really done is I've just kind of relabeled a couple of things. So once again, I'm going to come up with a formula for the slope of the tangent line. The only difference is I'm just going to label things a little bit differently. That's really all that I'm doing here. So yeah, so let me go ahead and start the process. So here we have, once again, some function, and I have some point C, and I have the tangent line to the graph of f at the point C, and I would like to write down a formula for the slope of the tangent line. Of course, we did this yesterday, but I'm going to come up with a new formula for the slope of the tangent line using just slightly different notation. The overall argument is exactly the same. What I do is I create a new point, okay, a nearby point, all right, this point over here. And, in the last video, I called this point X. I said its horizontal position was X. You'll notice that I wrote C plus H. That's a bit strange, but here's the idea behind this. Because this point here is just a little bit to the right of point C, that means that its X coordinate is just a little bit more than the X coordinate here. In other words, the X coordinate of this point has to be C plus some small amount, okay? And that small amount is what I'm calling H, all right? So you should imagine that H is just some small positive number like 0.5 or something, right? So if you take C and you add some small positive number H, you'll land here at a nearby point, okay? So I've got this nearby point whose X coordinate, whose horizontal position is C plus H. And of course, I've got the point on the graph, right, corresponding to that X value. And the Y coordinate of this point is, well, F evaluated at the X coordinate, right? So that would be F of C plus H. And just like last time, what I do is I create the line between these 2 points, between this point right here and this point right here. And I say to myself, well, the slope of the blue line right now, the solid line, does not look very much like the slope of the tangent line. But if I begin dragging this point to the left, if I bring this point closer and closer to C, then of course what happens, as it did yesterday, is the two lines begin to converge. And as this point gets very, very close to this one, the slope of the solid line turns into the slope of the tangent line. Now let me ask you, as I move this point closer and closer to C, well, actually, let me back up. So let me go ahead and write down the formula for the slope of the solid blue line, right? Just like I did yesterday. So, slope of the blue line, right? That's the solid line. Of course, it's rise over run. And the rise is the difference in the y coordinates, right? So the y coordinate of this point here is f of c plus h minus, and then the y coordinate of this point right here is just f of c. So that's the difference in the y coordinates of the 2 points. That's the rise. And then what is the run? Well, it's the difference in the x coordinates. The x coordinate of this point here is c plus h. And then the x coordinate here is just c. So if I subtract c, that will give me the run. The one thing that you might notice, though, is that in this in the denominator of this expression, there's some cancellation that happens. We have c plus h minus c. That just leaves you with an h. Okay, so this is a formula for the slope of the solid blue line, right? But of course, I want a formula for the slope of the tangent line, right? And just like last time, the idea is to simply, let this point get closer and closer to C. And as that happens, the slope of the blue line will turn into the slope of the tangent line. But now here's the thing. As I move this point closer and closer, what is actually changing? Like, what letter is changing? Is C changing? No, C is staying fixed. What's changing is actually H. Okay, remember that H is that little amount that we're adding to C to land over here. Okay, actually, H is actually the distance between these 2 points. If you notice that, right? Like if you're starting at C and then you go to C plus H, then H is actually the distance between those 2 points. Does that make sense? So as I bring this point closer and closer to C, what is happening to H? H is getting smaller and smaller, right? I mean, H is the distance between these 2 points, and that distance is getting smaller. So H is getting smaller and smaller. And what I want to do is bring this point closer and closer and closer and closer, infinitely close, infinitely close. And so what I'm really doing is I'm taking the limit as H goes to 0. So the slope of the tangent line will be obtained by taking this expression, which is the slope of the blue line, but allowing H to go to 0. So if I take the limit as H goes to 0, that will be the slope of the tangent line. Now, the thing is that, of course, we already have a formula for the slope of the tangent line, right? It's the formula that we've been using for the derivative, for the instantaneous rate of change, right? We already have a formula for the slope of the tangent line. It's limit as x approaches c, f of x minus f of c over x minus c. So because both this formula here and the formula that we derived yesterday, because both of those formulas represent the same thing, namely the slope of the tangent line, they actually must be equal, and they are. Okay, they give you the same thing. And so what that means is that I've got this one more algebraic expression to add to my list of things that all mean the same thing, right? So I'm going to open up today's worksheet. And so we now have this long list of things that all mean exactly the same thing. The instantaneous rate of change of f at c. That means the same thing as the derivative of f at c. Symbolically, like in notation, we use this expression to represent it. And as we saw yesterday, that means the same thing as the slope of the tangent line of f at c. And we can use this formula here to compute it, which is what we've been doing in the first 6 days of this course, or you can use this formula right here, which I just derived, okay? And I know that I can use either one of these formulas because they both compute the same thing. They both give you the slope of the tangent line, so they must be equal. Typically, this definition, the one that we've been using, is sometimes called the first limit definition of the derivative. And this one here, the one that I just derived, is called the second limit definition of the derivative. I promise that if you use either one of these limit definitions, you'll always get the same thing. It doesn't matter which one you use. However, I will say that the second one is, it's typically a lot easier to work with. And as a matter of fact, I've got to say that outside of like AP Calculus, like when you go to college and stuff, you pretty much only see this definition. This one's kind of nice. It's kind of easier to explain where it comes from, I suppose. But this one's just much easier to actually work with. So yeah, you'll probably work with this one a lot more when you actually take calculus. Anyway, so we're going to do just, we're basically, the goal for today is all you're really going to do is you're just going to practice using this new limit definition of the derivative. And so I'm just going to do an example with you using that new definition, okay? So example, what I'd like to do is I'd like to let f of x be the function x squared plus 3x. And what I'd like to do is use the second limit definition of the derivative. To find f prime of 4. Okay, so I'd like to find the derivative at 4, or if you like, the instantaneous rate of change at 4, or if you like, the slope of the tangent line at 4. All that stuff means the same thing. Okay, but I'm going to use this new limit definition. Okay, so let's recall. So what is the new definition? It says that f prime of c is the limit as h approaches 0, f of c plus h minus f of c all over h. That is the new limit definition, right? But of course, I don't want the derivative at some mystery point c. I want to know the derivative at the point 4. So of course, what I have to do is I take this definition and I replace all of the c's with 4s. Okay, so f prime of 4 is going to be the limit as h approaches 0, f of 4 plus h minus f of 4 all over h. And now it's basically an algebra problem. I just have to, figure out what this expression is and probably simplify it, and then I'll be able to find the value of the limit. The one troublesome point is that a lot of students don't have much experience evaluating expressions like f of 4 plus h. In fact, they tend to look at that and they get a little bit confused. They're perfectly fine with like f of 4. They're like, I know what that means. F of 4 means I just plug 4 into the function. Like I replace any x's that I see with 4s. They get that. But they see the 4 plus h and they get a little confused. Okay, but the idea is the same. F of 4 plus h simply means you go to the formula for f and you replace any x's that you see with 4 plus h. Okay, it can get a little complicated. And so I think that what I'm going to do is I'm actually going to figure out what f of 4 plus h is separately, like on the side here. And then I'm going to figure out what f of 4 is, like also separately on the side. And then I'll come back to this expression. Okay, and I'll plug them in. So let's start with f of 4 plus h. Like what is that? So as I said, you just go to the formula for f, and any x's that you see, you replace them with 4 plus h. So first you have x squared, okay? That means that you need 4 plus h squared. And notice that I've put the 4 plus h in parentheses. That's because, like, if I'm replacing x with 4 plus h, and x is squared in the original formula, that means that all of 4 plus h needs to be squared, okay, in this expression. And then plus 3x, but I'm replacing the x with the 4 plus h. And notice again, I put the 4 plus h in parentheses. And the reason for that is the following. In the original formula, 3 is multiplying x, right? If I'm replacing x with 4 plus h, then the 3 had better be multiplying all of 4 plus h, not just part of it, like not just the 4, but all of it. Okay, so that's why you need the parentheses here. So the 3 multiplies all of 4 plus h, because after all, 3 certainly multiplies all of x, and I'm replacing x with 4 plus h. So the 3 had better multiply all the terms of the thing that I'm replacing x with. Okay, so what is this? Now, by the way, I hope there's a really common mistake here. Students, I think I've probably already mentioned it in this course, but when students see this 4 plus h quantity squared, they very often just say to themselves, oh, 4 plus h squared, that just means I square each thing. That means I square the 4, which is 16, and then I square the h, and that gives me h squared. And guys, that is not true. That is not how it works. Unfortunately, exponents just cannot be distributed in that way. 4 plus h quantity squared, when you square something, it means you multiply it against a copy of itself, right? So 4 plus h all squared means you're going to take 4 plus h and multiply it against a copy of itself. That's what 4 plus h squared means, okay? Plus 3 times 4 plus h, okay? All right, so what do we do now? I mean, we need to simplify this, right? We need to multiply all this stuff out. We need to multiply all this stuff out. We need to distribute the 3, and then we're going to have a bunch of terms, and we need to collect the like terms, put them together. So 4 times 4 is 16, plus 4 times h is 4h, plus h times 4 is, again, 4h, plus finally h times h is h squared. So these 4 terms here are what you get from this. And then plus distributing the 3 times 4 is 12, plus 3 times h is 3h. Okay, so like I said, we get a bunch of terms, but they now need to be combined, right? So, and I think I'll put, so how am I going to rearrange the terms? I like to put the squared term first. That's kind of by convention. So I'm going to put the h squared first. Notice I kind of underlined it. This is a good habit. When I'm combining a lot of terms, like there's like 6 terms here, I like to underline terms after I've sort of already accounted for them in the next line. That way I don't like lose any of them. What else do I have? I have a 4h here and a 4h here. Those can be combined to give me 8h. But then there's another 3h here, and that can be combined as well to give us a total of 11 copies of h. So that'll be 11h. And then what's left over is the 16 and the 12. And that's going to, 16 plus 12 is 28. Okay, so this expression right here, that is f of 4 plus h. Okay, now, I mean, remember that big picture, what we're trying to compute is this whole expression right here. All I've done is I've computed just the f of 4 plus h, right? And it's given me this guy right here. Okay, well, now I need to compute f of 4. Fortunately, that is a lot easier to compute. That will not take a long time at all. So what is f of 4? Well, we just need to plug 4 into our expression here. So it's 4 squared plus 3 times 4. Okay, so that's 16 plus 12, which is 28. Okay, so now that I've computed these two things, I'm actually going to go back to the limit that I was actually trying to compute a moment ago and sort of replace, right? I'm going to replace the f of 4 plus h with this whole crazy expression, and I'm going to replace the f of 4 with 28. Okay, so I have the limit as h approaches 0. Okay, so f of 4 plus h, we agreed that that was this thing right here, h squared plus 11h plus 28, and then minus f of 4, which we said was 28, all over h. Okay, so now we're going to try to actually evaluate this limit. As usual, if you try plugging in the number, you get 0 over 0. Like if you just replace the h with a 0, the whole numerator will be 0 and the bottom will also be 0. So this thing needs to be simplified. An obvious simplification that can be done is this right here. 28 minus 28, that's nothing at all. So that's limit as h approaches 0 of just h squared plus 11h over h. But there's still more simplification that needs to be done. What can be done is the numerator can be factored, right? There's a common factor of h in these two terms, and I need to pull out that common factor. So, so I have the limit as h approaches 0, h times h plus 11, right? So I've pulled out that common factor of h, and now I can do some cancellation. Namely, I can cancel this h right here with that one right there. So those will cancel, leaving me with the limit as h approaches 0 of just h plus 11. And now my expression is totally simplified. If I replace h with 0, you get something reasonable. You get 0 plus 11, which is 11, and that's the value of the limit. Okay, so the derivative of this function at 4 is 11, or if you like, the instantaneous rate of change of this function at 4 is 11, or if you like, the slope of the tangent line of this function at 4 is 11. They all mean the same thing. And yes, I used this definition to get it, but I could have also used the other definition. Like, if I had, if I'd used the old definition of limit x approaches c, f of x minus f of c over x minus c, that would give you the same answer, right? I mean, c in this case is 4, so it would be the limit as x approaches 4, f of x minus f of 4 over x minus 4. I promise that if you compute this limit, you will also get 11. Doesn't make any difference, okay? Okay, yeah, so the worksheet has some practice problems where you kind of get some experience with evaluating expressions like this, like f of 4 plus h, because it is pretty tricky for a lot of students, but that's it for today. And so we have finally gone over all of the interpretations of the instantaneous rate of change that I wanted to go over. There are other ways of understanding and interpreting this concept beyond what we've talked about, but we won't really get into them in this course. So, okay, that's it for today. See you guys next time.